Okay, let's get started. All right. Today, we will begin our discussion of SQL, the structured query language, sometimes pronounced SQL. You can say it however you like. Just a bit of review from last time. We talked about the relational algebra last time in some detail. And remember, it has a somewhat operational semantics where you compose essentially a tree or a nested description of operators to answer a query. So it's sort of step by step. It's just that the steps are these big set-oriented tasks, right? Big disorderly set-oriented tasks. And then the nice thing about the relational algebra is it corresponds quite nicely to our notion of query plans and iterators, but it gives it a formal grounding that we'll be able to use for optimization. We also spoke but did not look at the relational calculus, which has a declarative semantics. So rather than having an order of operations at all, you simply describe in logic what the answer set shall include. I would like all tuples such that blah, blah, blah. And you don't say anything about how to achieve that result. The sort of algorithmics are left to the computer, and the programmer, if you will, is really just specifying a description of the output in syntax, in logic, which is a crazy, audacious thing to do, right? Step back for a minute and imagine that I told you that from now on you will no longer write Java or Scala or Python. You will simply describe the outputs of your programs. You'd say, well, that sounds really hard. That seems crazy. But that's actually what SQL is about. For at least a limited set of tasks, that's exactly what we're saying. We're going to say, from now on, everything's declarative. We will only describe the outputs of things. We will not talk about how to achieve them. And computers, with all their smarts and extra cycles, will figure out a good way to go execute the tasks we want them to execute. This is happening increasingly up the language stack, I would say. Declarativity is creeping into your programming languages more and more. And it sort of the most well-studied and mature example of this is SQL. All right. So relational calculus has this flavor of declarative semantics. These two things are simple and powerful models for query languages, but rather than look at the calculus, we're going to look at SQL as a much more widely used and easier to learn declarative language. All right, a note, and this is review again on expressivity. An important question you should ask with any language is just what is sayable in that language. So in a query language in particular, they're often not Turing complete. So you can't say everything you can say in C or assembly language. So what can you say? It's a question of computational complexity. What's the class of algorithms in terms of complexity typically that you can say with the query language? Now SQL is actually a very powerful language. So you can even say exponential things in SQL. But the basic relational algebra, for example, can't even say all of polytime. Okay. So depending, maybe if you have subtraction, it can, actually. I take that back. Maybe it can say all of polytime. Oh, boy. But in any case, it can't say exponential things. So there's a question here of kind of how much you can say, and oftentimes the way we talk about that is what category of algorithms can we describe. So Codd's theorem said that the algebra and the calculus have equivalent expressive power. What that means for us is that we can take declarative statements, a la SQL, all right, and we can compile them down into operational statements, a la query plans. All right, so this pointed the way towards being able to take these high-level declarative statements and have a natural implementation for them. SQL is more powerful than the relational calculus, okay, or the relational algebra, therefore. But it can be captured with a set of operations and a way to string them together that looks a lot like the algebra. The iterators we have in our relational databases look a lot like the relational algebra. So you don't have to go a lot further than the bones of the algebra to get all of SQL. One key difference that we'll see today, there are others, but one key difference is that the SQL by default, we're going to be dealing with multi-sets of records rather than sets. So each record can appear more than once in a relation in SQL, and we're going to care about that and account for it in all of our operations. Okay, and we may not talk about that in a ton of detail today, but it's going to be lurking there in the background. All right, just to give you a picture of how this stuff works in practice, typically you sit down and you write an SQL query. The query optimizer is going to go off and generate potentially many relational algebra expressions, query plans, if you will, that could execute that query. And they're all equivalent. So all of them will produce exactly the same answer, modulo, say, the order of the output. And so the goal of the optimizer is to pick the cheapest one. And later on in the semester, we'll talk about how it goes about this process. But I want you to be very conscious of the fact that there's a large number of possible execution strategies for your simple SQL query, and you don't have to think about which of them is best. Okay, inside of SQL, there's sort of two sub-languages. There's what's called the data definition language, the DDL, and that's for doing things like setting up tables and modifying them, all right? Creating the schemas for tables and altering the schemas for tables, defining constraints on those tables, which we'll talk about a bit today and much more later this semester. But the juicy bit, the part that we're going to look at today, is the data manipulation language, the DML, where you can write queries. Okay, so that's the piece of SQL that we'll be interested in today. The database management system is responsible for the efficient evaluation of these declarative queries, right? And the key to being able to do this is having the semantics for the queries, and Codd's theorem pointed the way towards the idea that you could unambiguously map from a declarative query to one of many possible operational plans. The optimizer is free to reorder the operations in these plans without affecting the query answer. And the rules for those optimizations, which one of you asked about last time, those rules will come clear over the course of the next few weeks. Okay, so today we're going to talk about SQL, and we'll continue with this on Thursday. It's going to take at least 2 lectures to get through all the material in SQL that I want to get through. So we're going to do more than just sort of standard stuff. Why teach SQL? Well, it's the most widely used query language, other than, say, search, than free text search. So it's not just the most widely used relational query language, it's really the most widely used query language. It's well standardized and has been for a long time, so the core of it is something that is shared by most database implementations. Although most systems also add some extra bells and whistles, which are idiosyncratic. Postgres is an example of that. And then there's some recent systems, things like Spark SQL and Hive, actually, in the big data space, where the SQL isn't quite compliant because those systems are actually just so young that they haven't been pressured by their customers to comply with standards. But I fully expect that they will become closer to the SQL standard over time. So learning SQL is a very, very safe bet. In this class, we're going to study the basic constructs. We're not going to learn every corner of this language. It's a very big language. Ironically, it was designed to be a very little language, and the guys at IBM who designed it, I know them, they said that they're sort of horrified at what happened to it. It was supposed to be something that, say, an auto mechanic on the garage floor could go get some parts from. It's supposed to be easy to read and easy to type, and it's turned into something that's really quite powerful. What you'll see even today, though, even on the subset we're going to look at, which leaves out all sorts of esoterica, like how do you deal with geographic data and how do you add user-defined functions and so on and so on. What you'll see today is that there's a bunch of subtleties that arise through things like duplicates and multi-sets and things like set minus, actually, and various forms of that, which complicate the language in subtle ways that make it a little testy. So we'll have a look at it today. All right, here's our little example database. We're going to have 3 tables, and they've got instances, so these relations actually have data in them. And I went ahead and typed these into Postgres last night, so we'll be able to run some queries against this stuff ourselves. Sailors, boats, reserves, all right? And just so you believe me and make sure I didn't screw up last night. Oh, come on, full screen for me, please. This is going to be annoying if I have to do this every time. Is that it? No, that's the wrong window, that's why. Oh, come on. Where's my Postgres window? And by the way, Postgres is set up for you inside your VMs, and I definitely encourage you to go ahead and try this stuff out at home. Everything in the slides as of last night pretty much cuts and pastes directly, and it works correctly. So here we go. Here's our tables, all right, \d, and the Postgres prompt gives tables, and then if we want to look at one of them, let's make sure our data's there. There's boats and sailors, and let's make sure there's some reservations. Awesome. Okay. The reservations are in the future, which is kind of interesting. That's an accident. Okay, so here we go. So the DDL to create these tables, all right, we're just going to learn enough to get you dangerous on the DDL side. It's not very interesting anyway. We're going to be able to create a table called sailors. You give a list of columns and types. Types come after the column names. So SID is an integer. SName is a character array of width 20. For reasons that are somewhat historical and somewhat for performance, it's sometimes good to fix the width of your fields, a maximum width, just so things are more compressed on the disk. If you just say text all the time instead of character with how long it is, then the system will not be able to have fixed length tuples and pack things as tightly. All right. The one thing that you should note here, this DDL with real is probably wrong. That should probably be float. But beyond that, primary key SID is an important detail. So we're going to have what's called a primary key for this table. We'll talk about this more later. But basically what we're saying is the SID column contains a unique identifier for every row. And there can be no duplicates in the SID column. That's what that primary key syntax says. And as we talked about previously, you can have multiple columns in the primary key, like last name, comma, first name could be a primary key. Okay? So the primary key is actually a list of columns. All right, here's the boats table. It's got a primary key called boat ID or BID. And then here's the reserves table, and it's got a primary key, interestingly enough, which is all three columns. So each sailor, each boat, each day, that's unique. So a sailor can only reserve a given boat on a given day once. There are no duplicates in this table, is what that's saying. Okay? And you can set that up in the system. It will guarantee that these constraints about primary keys remain true. If you try to insert a duplicate, it will reject your transaction. Okay? All right. So you can think of these identifiers in this little schema here as pointing to each other. So the BID of reservations will point to the BID for boats. The SID for reservations points to the SID in sailors, right? We'd like to formalize that with the system. We'd like these pointers to always be true. So we're going to tell the system about these in the DDL for the reserves table. We're going to say that SID in the reserves table is a reference to sailors. We call that a foreign key. And we're going to say that BID in the reserves table is a reference to boats. Okay, so the syntax is foreign key, set of columns, references table. Now notice that we didn't say which columns in the sailors table it's referencing or which columns in the boats table it's referencing. Because it's referencing the primary key columns of those tables, all right? So that's the syntax here. Is when you say references table, you have to have something that is the same type and the same number of columns as the primary key of the table you're referencing, right? Another way to think about this is how do you address the sailors table? How do you identify a unique sailor? By SID, because that's the primary key. So references to sailors must also reference SID, right? So think of primary keys as addresses if you want, and the types of those addresses have to be used elsewhere. Okay, so there we have a table. And by the way, now the reserves table can only contain reservations for real boats that exist in the boats table and real sailors that exist in the sailors table. All right, and this will be guaranteed again by the system. If you try to mess with those references, the system won't let you. All right, so here's our first little query. We've done this in single table SQL earlier in the semester, but we'll go through it methodically today with the book. So find all 18-year-old sailors. Select star from sailors as S, where s.age equals 27. Sure, we could go do this in Postgres if we want, but let's maybe not right now. Should we? No, it's too hard to copy-paste from these slides. All right, we're pretty clear what's going to come out of that. It's going to be Nancy. And if you didn't want to get all the columns out, you could list which columns you wanted in the select list, and we've seen this. Moving on to join queries now, and I've been doing this on the board, but we haven't actually had time to study it. We're going to talk about how to express joins a bunch of different ways today. Here's a reasonable way to express a join. We're going to select s.sname from sailors as S, reserves as R, okay? So we're going to take the sname out of sailors, where s.sid equals r.sid. That's our join predicate. It's going to say we're going to match up things in the cross product if the SID of sailors equals the SID of reserves, and r.bid equals 102. So I want the name of sailors who reserved boat 102, right? All right, and this one maybe real quickly. We'll just run this in Postgres. And there's Fred and Jim have both reserved 102. Let's see if we believe that. Fred is SID 1, Jim is SID 2. Let's look at reserves. Oh, yeah. That's not. Oh, it looks great over here, though. Sorry about that. Rather than mess with the display, which has been a challenge all along, let's just do this. Let me shrink this. Like that. This should be reliable from here on, I think, for the rest of the lecture. Good. Aha. There's Fred and Jim. All right. There are the reservations at the top. Fred is sailor 1, Jim is sailor 2. They've both got 102, so this looks like the right answer. Great. Okay, going back to the slides. Generally speaking, we've seen this before, but here's some of the naming conventions from the book. Your basic SQL query is this block select distinct target list, which is this list of expressions over the attributes of the table in the relation list. The relation list is a list of relation names, possibly containing these range variables, which are the variables we put after the as clause, right? So sailors as S. I will point out the word as is not necessary, actually. In that particular location, you can say select star from sailors S, where S dot something equals. The distinct clause obviously is optional. It's whether or not at the end we remove duplicates. And the qualification in the where clause, as you know, can be pretty much any Boolean expression you like over the range variables. Okay. Now, the query semantics for a given query like this are pretty straightforward. And they kind of work inside out. So you start with essentially the from clause. And the first thing you want to think about is the cross product of all tables. And then over that cross product, we evaluate the where clause to check conditions and discard tuples that do not pass those conditions. And then the select clause removes any unwanted fields and computes any expressions that you want to compute. The distinct clause, which is optional, eliminates the duplicate rows. Now, obviously, this is a lousy way to execute these queries, and a query optimizer will use join algorithms to do something better. The more general flow, though, with group by and having kind of looks like this. Think about the from clause, then the where clause, then the select list, and then think about group by and having and distinct. Okay. So generally speaking, when I read an SQL query, I start sort of along these lines. I look at the from clause and the where clause first, and the select third. And I'll say that when I was doing the solutions to your next homework last night, this is exactly how I wrote them. I said select, and then I hit return in my editor and started doing the from and the where, and then went back up and did the select and the group bys and all that stuff later. Okay. So this might be a useful flow to think about when you're thinking about your queries. Find the cross product, apply the selections, project away any columns that aren't needed, keeping only those remaining in select, group by, and having. Form your groups and aggregate, so that's the aggregates in the select list. Use having to eliminate any groups that don't qualify. Use distinct to eliminate any duplicates in the output. Okay, and with that, let's start looking at some queries. We did this last time in relation to algebra. Today we're going to do it in SQL, all right? And they're going to get progressively more interesting as we go. Find sailors who've reserved at least one boat. Well, it's going to be a select from where block, okay? And it's going to involve the sailors table and the reserves table, right? All right. Now, what are we going to join on? SID, right? There's an SID in sailors, there's an SID in reserves. It's that key foreign key relationship, right? Where reserves references the primary key of sailors. All right? And so what we've got out now are pairs of sailors and their reservations. Clearly, any sailor that has a reservation has reserved a boat. So we're kind of done, right? We just need those SIDs. That list of SIDs are sailors who have reserved a boat at least once, maybe more than one. Would distinct make a difference in this query? If we said select distinct, shall we try it? I'm actually not sure in the database we have whether it'll make a difference or not, but let's try it. So let me copy the query. Oh, this is the one that doesn't copy nicely. All right, we won't do that one. This is the only thing that I formatted where it's hard to copy because I wanted to do this silly animation. Do duplicates make a difference? Anybody? Could we possibly have duplicate sailor IDs in this query? Yeah. Good. So sailors .sid is a primary key. So each sailor can only appear once. That might lead us to believe there's no duplicates. That's good thinking. Do you all agree? No duplicates possible in this query? I see some heads shaking no. You want to fill us in while you're shaking your head no? Right. We're going to join up that sailor's SID with one of possibly many reservations for that sailor, leading to multiple records in the output. In essence, when you do a key-foreign key join, the table with the foreign keys, that is the reserves table in this case, is going to dictate how many copies of each key appear. There's going to be one output for every reservation in this case, because the sailors are just a lookup in essence. You look up the detail per sailor. But the reservations could have duplicates on the SID. So this could have duplicates, and distinct would indeed make a difference. And I very strongly encourage you to go play with this in the database and insert reservations for multiple sailors. And you'll see that you get multiple SIDs out for those sailors. Okay? All right. A note about range variables. We actually need them sometimes. They're not just for convenience. Because sometimes you want to join a table to itself. And then you need to be able to have two different loop variables, if you want to think of it that way. They're called range variables for the table. So here's an example. What are we doing? We're joining sailors to sailors. One version of sailors is called X, the other is called Y, where X.age is greater than Y.age. And we want the name of the X sailor and the age of the X sailor, the name of the Y sailor and the age of the Y sailor. What's going on here? What is this? These are pairs of sailors where one is older than the other, right? It's sort of the dominance of sailors. And the output of the query, this query we can do in the database. So let's just have a look at it. There we go. Here we go. Right? Jim is older than Fred. Jim is older than Nancy. And Nancy is older than Fred. Okay? That's all perfectly reasonable. But the point of this all was sometimes you do self-joins, and in your homework you will definitely be doing some self-joins. Very natural thing to do, particularly when you're trying to find relationships between objects within a single table. Right? In some sense, what you're doing in all these cases is forming an edge in a graph. Right? This is the older than tree, or if you will, right? Or DAG, partial order. So we're forming an edge between one sailor and another sailor where one is older than the other. Okay, you can put arithmetic in your SQL both in the select clause and in the where clause. All right? And if you're bored and you don't have a calculator handy and you need to add some stuff up, SQL actually allows you to just type at it without a table name. Come on, where'd it go? This is truly annoying. Okay, well, here it is. I don't know how it chooses whether it's in mirrored or not. But you can say select 100 times 3, and it'll give you the answer. All right. You can say select, I don't know. There's a whole bunch of functions. There's a whole expression language, cosine of 1.2, etc. Okay. So if you don't have a table, you just get a default one-row table as your input, and it'll essentially generate you an output. And you can do this in the where clause as well. You can say select star from sailors where, age times 2 equals 4. And that, I'm sure will have nothing in it. All right, you get the idea. Okay. String comparisons. So SQL kind of predates the widespread adoption of regular expression standards. So it has its own annoying pattern language and a command comparator called like. Okay, so this is sailors whose name is like Bob or Borb or anything else you can put between two B's. Okay. Underscore is like the dot in regexes. It's any one character. Percent is like the star in regexes, 0 or more arbitrary characters. There's usually another syntax in most systems for using regexes instead of like patterns, okay? And Postgres has that. Most systems do. I forget what it's called. You can look it up. So if you prefer regexes to this weird SQL-like, you should do that. And frankly, regexes are better. Like is pretty limited. But it's there. You can do string comparisons. All right. Now, We may remember this query from relational algebra. All right, let's look at a little Boolean logic. Find SIDs of sailors who've reserved a red or a green boat. So here's one way to do it. Select from boats and reserves, join on boat ID, right? So for every reservation, look up the appropriate boat. And boat.color equals red or boat.color equals green. So this should work. And let's just double check that it does work. If I can. Copy. And paste. Oh, there's 0 rows. That's rather disappointing. In the sample data, there's no answers. But it is the right query. All right, here's another way to express the same query. Find the red boats, find the green boats, and union them. All right, and the union syntax in SQL is just you put a SQL block above it and a SQL block below it. Note, by default, union in SQL removes duplicates. If you want to preserve the duplicates, like there's 2 here and there's 5 here and you want 7 in the output, you say union all. All right, ALL. But by default, it will remove duplicates. Find SIDs of sailors who've reserved a red and a green boat. You remember this from the relational algebra expression, right? So this is going to find all the reservations. It's going to look up the boats. And then for each boat, if its color is red and its color is green, it will be in the output, except there is no such boat, right? No boat can be both red and green. So instead, you want to do the intersect query, right? That's equivalent. And this will get you sailors who've reserved a red boat, sailors who've reserved a green boat, and the intersection of their SIDs. There's yet another way to do this in SQL. We could do it with a self-join. All right, so let's see how this looks. What I want is pairs of reservations, R1 and R2, such that R1 is for a red boat, R2 is for a green boat, and both reservations are from the same sailor. Right? So that first clause makes sure that both reservations are from the same sailor. The second and third clauses in the where just connect the boat details to the reservations. B1.bid equals R1.bid, right? And the last clause checks that the left-hand boat, B1, is red and the right-hand boat is green. Okay? And then we got an output which could have had the pairs of red-greens for each sailor, but we just projected it down to SID and we just got out the sailor IDs. Okay, so this query in some sense does a little bit of extra work. It actually pairs up those red-green pairs that are evidence of such sailors, but then we throw those pairs away and we just keep the SID. Yeah?
Will this print out duplicates for names if like a sailor had two, if he rented like 2 red boats and 1 green boat?
Yeah, actually this will do a bunch of duplicates, right? Anytime there's a sailor who has, let's say Bob rented 1 red boat. No, let's say Bob rented 2 red boats on 2 different occasions and 3 green boats. How many times will Bob appear in the output? 6 times, okay? With every red-green pair, that's evidence that he rented both. So good question. This will definitely have lots of duplicates. It'll have kind of almost per sailor cross-ID style duplicates, cross-product style duplicates, excuse me. Make sense? So if he had 2 green reservations, 3 red reservations, he's got 6 pairs of red-green. All right, and again, I encourage you to punch in some sample data into Postgres and give it a try. There's nothing like hands-on experience. All right, not in kind of detail. So find SIDs of sailors who have not reserved a boat. Well, let's take all the sailors, and then let's do set minus, which in SQL is called except. All right, and we'll find the sailors that do have reservations. Make sense? Now, except, like union, doesn't care about duplicates. It removes them. All right, you'll notice that SIDs only appear once in the top, but we said earlier that bottom query could generate duplicates in the SID if there's multiple reserves. Because we just said except, it doesn't matter. It doesn't matter how many duplicates there are on the right-hand side. It's as if there's only one of each on either side, and you keep things from the left-hand side where there's no matches on the right. There is an except all in SQL. So you can take this query and you could replace it with except all. All right, and I would encourage you to try that and see what happens. All right, and populate it with different amounts. Make sure you have different amounts of reservations and different duplicates on the outside and see what happens. Okay. So the multi-set cardinality, which is to say how many copies there are of a record in these multi-sets, is something that's going to appear in all your SQL queries. Here's another way to say this sort of notion of things being in stuff. So we talked about intersection. Now let's talk about a predicate called in. This is a different construct in SQL, typically called a subquery. So we got an outer query, which scans the sailors table. And for each tuple in that sailors table, we're going to run a subquery that's going to look up some stuff, and then we're going to compare to see if the outer tuple is in the result of the subquery. Okay, so for each sailor, we can think about running a query on reserves for boat ID equals 102, and we'll output those sailors who've reserved boat 102 that way. Okay, so the subquery is not joined in. The subquery is checked for every tuple of the sailors table. And in this case, you can imagine that the smart execution of this executes the subquery exactly once and stores the output, and then runs the outer query and looks in the output of the subquery for matches. Okay. And you can do the same thing with not in, which is a little bit harder to say with a join. In fact, I defy you to say it with a join. Okay. So now we can find sailors where SID is not in. These are sailors who have not reserved boat 103. Remember what I said about the relational algebra, that set difference was the only non-monotonic operation. It's the only thing where when a new tuple comes in, the answer could actually get smaller. So sailors who have not reserved a boat is non-monotonic. If you get more reservations in, you get fewer sailors in the output, right? And so not in is clearly not doable with just joins and selects and projects. It needs to be some kind of set minus, right? So not in and except are very related to each other. They're both non-monotonic set minus-y kinds of things. In, on the other hand, usually can be rewritten as a join because it's truly monotonic. Right? Add more things to reserves, you get more answers. Add more things to sailors, you get more answers. Okay. Now, here's a nested query that's a little more puzzling. So here, what we're going to do is we're going to, first of all, another clause. Instead of saying in, you can say exists. Okay? So you can say select star from sailors where there exists a tuple in some query. And if that query is non-empty, then the outer tuple goes to the output. So specifically, I want sailors who've reserved boat number 102. So let's look at this. Select S-name from sailors where there exists something in the subquery. What's the subquery? Select star from reserves where reserved up boat ID equals 102. And look, there's a reference to the outer query comparing against this inner query's tuples. So in this case, because of this reference to S within the subquery is kind of different for every tuple of the outer query. You have to pass in the SID, sort of like a function call, into that subquery. That subquery is parameterized by s.sid, which means that you do really have to run it once per tuple of sailors, assuming every tuple has a different SID, which it does. Okay, so this is not a case where you can pre-compute the subquery and just check its answers. Here you're really running the subquery once per tuple of the outer table. Does that remind you of a join algorithm we learned? For every tuple of sailors, scan through all the reserves looking for a match. What algorithm is that? That's a nested loops join. It's a naive nested loops join. It's a per tuple nested loops join. This is a terrible execution strategy, all right? So a good database system will look at this thing and go, I bet I can rewrite that as a join and use hash join or sort merge or at least page-oriented nested loops. Right? But the way it's actually expressed in SQL, even though SQL is sort of supposed to be declarative, it has a flavor that seems to imply that the binding values of the variable s.sid are delivered once per tuple of the outer table. So most systems will rewrite this query into a join one way or another. But here's a detail that you have to think about. How many duplicates are in the output of this query? Well, it's a query on the sailors table. The subquery is just a condition in the where clause. Okay? So the sailors table, for every tuple of sailors, it's either in the answer or it's not in the answer. All right, so there's going to introduce no duplicate sailors in the output. So each S name will appear as many times as it appears in sailors. All right. So interestingly, this exists clause doesn't actually generate an output tuple per match. It just says, are there any matches? Does a match exist? And then it outputs only one. So the duplicate semantics for this are different than they would have been if it was a join. If it was a join, we would have had one copy for every reservation. Instead, here we only have one copy for every sailor. So unfortunately, when you rewrite these things, you do have to worry about the duplicates and respect what the user asked for. Okay, so systems that rewrite this under the covers have to be really careful to make sure that the duplicate semantics are preserved. All right, a couple more set comparison operations to think about. We've seen in and exists in the examples in the previous slides. And let me write up on the board the template of these things. So the subquery template is, select stuff from tables where, some tuple variable, so let's say some tables, and one of them is as t, where t dot, value comparison subquery. So this comparison is a comparison between a value, something of type like integer or float or string, and a set of tuples. All right, that's the type of these comparisons. So the comparisons can be things like in, right, value in table. All right, and if that's true, the table had better have only one column, and it better be of the right data type. All right. So if this is an integer, this better be a table of one column of type integer. Same with not exists. So there's not exists, there's not in, as well as exists and in. And then exists doesn't have this at all, right? Where exists. It doesn't actually need an outer value here because it's not a binary, it's a unary operator. You can also say operator any and operator all. So like equals any. T.value equals any value in this subquery, all right, which is a lot like exists. But if you had greater than any, it would be different than exists. Okay. So you can have any Boolean operator there. So let's look at an example of that. Find sailors whose rating is greater than that of some sailor called Fred. All right. Find sailors whose rating is greater than any rating of a sailor called Fred. Okay. Everybody good? All right, we're about to do a more interesting one, so let's take a break. Everybody stretch. Hello. All right. So here's a hard query. There's actually something I didn't bother to teach you because it's annoying that we're going to see in SQL. But in relational algebra, there's actually an operator called this. It's a macro. All right. So it actually isn't required in the algebra, but it's a weird little macro called division. So relational division is find all the things such that, well, I'm going to get this wrong off the top of my head. This is a relational division query, though. And what we're going to do is we're going to see it in SQL, and you have to block it out in pieces to get it right. Seems like a harmless little query. Find sailors who have reserved all boats. All right, so sort of sailors divided by boats. But find sailors who have reserved all boats. So here's how it's going to work. This is actually the answer, or an answer to that query. Doubly nested, not exists. All right, let's go through what's going on here. Find sailors S, that's the outermost query, where there does not exist a boat B that is missing a reserves tuple showing that S reserved B. It's a double negation, all right? And this is actually how you define division. To find the sailors who've reserved all boats, you find the sailors such that there is no boat B that they haven't reserved. All right, it's a pretty horrible little query. This comes up. Like, this is a thing you might have to do now and again. All right. Anyway, this is fun. If we did relational division, you'd say, wow, yeah, I've seen that one before. But anyway, here's how you do it in SQL. All right. At this point, we're going to sort of drop a little bit off of the edge of the relational unordered semantics. All right. It's sort of great a lot of the time that relational query languages are about sets and multisets, because it means we can parallelize stuff and we can do things out of core because we don't care what order things happen in, right? So the order of the set at the output doesn't matter. So if we want to like spill some tuples to disk and deal with them later, that's fine, because it doesn't matter what order things happen in. If we want to split things up and run them on multiple machines, those machines can run independently at whatever speed they want, because it doesn't matter what order the answers happen in. All that stuff is great. Every once in a while, though, you want to ask a question that's fundamentally about order. Like, I want the most popular thing. All right? Sometimes called the argmax query. I want the thing that is the maximum. All right? So I want the sailor with the highest rating. And you can worry about the ties thing before. And you can do it in SQL. It's just kind of obnoxious. So you can say, I want the sailor such that their rating is greater than or equal to the ratings of all other sailors. All right? That is, in fact, the sailor with maximal rating. All right? Here's another way to say it using an aggregate. I want to find the sailor whose rating equals the max of ratings. All right? Notice this is weird. This is actually a use of equality with the subquery. S.rating equals subquery. So from a type perspective, this doesn't seem right. This is a integer equals set of integers, or really set of integer tuples. Seems broken. And this only works because it's a max query with no group by. So it has exactly one row in the output. And so really it's just a tuple containing an integer, which you might as well just unwrap and treat as an integer. Okay? If you had a group by in that select clause on the interior in the subquery, this would be illegal, and it would get rejected by the parser. But because you can tell from the syntax of that subquery that it returns exactly one row with exactly one column of the right type, this equality is actually legal. Okay. All right, but here's the way you really want to run this query, which is cheating from a pure relational context, but is the obvious thing to do if you're like a normal person, which is find all the sailors, sort them by descending rating, and give me just the first one. Okay. So this works. This limit clause is there in SQL. It works. It's supposed to be sort of just for display. Okay. In particular, you can't put a limit in a subquery. Okay. So if you actually, for some reason, needed to find the maximal sailor and then do something with it, you can't do that, I don't believe, in a subquery. This is really only at the outermost level, and it's supposed to be just for display because, after all, everything's just a set. So order by should only be at the outermost level. Okay, but this is the obvious thing you want to do lots of times. You will very likely use limit clauses all over the place when you write queries in the real world. Sorry, which subquery do you want to run? Top right, select max S2 dot rating from sailors. You can do that. That query? Make sense? Let's look at the sailors table to make sure we believe that. 8's the biggest thing in the rating column, right? Okay. Everybody good? Okay, so this limit clause is a little bit of a hack in some sense. It's not really robust. You can't nest it inside of other queries. Okay, here's another thing that's complicated about SQL that kind of makes your head scratch a lot. And it has everything to do with horrible stuff like is an in query the same as a join query? And nulls cause a lot of headaches. But it was considered a useful thing, and it's in many of your programming languages as well, for every data type in SQL to have a null value, which means, I don't know. It means it's uninterpreted. So doesn't necessarily mean missing. It doesn't necessarily mean it's not any given value. It just means I don't know. You can think of it as a value that hasn't been filled in yet, if you want. Okay? So there's a special null value in every data type for this, but it makes it annoying when you're doing querying, so in a bunch of ways. So first of all, in your where clause, if you want to check for nulls, you have to say where value is null and where value is not null. All right? Equality predicates we'll talk about in a minute, but you can't say equals null because null is not a value. Null is a missing value. So you can't say equals null. You have to say is null. Assume that you have a rating that actually is null. Okay? So let's try this out. If you have a predicate rating is greater than 8, and you have a sailor whose rating is null, what do you think should be going on here? If I do that, then I get the big one. All right. So let's insert into sailors values. S84, we will name this sailor Popeye, and we'll give him a rating of null, and we'll give him an age of 100. He's an old sailor. Okay, so we want to know the question if rating greater than 8 applies to Popeye, where rating is greater than 8. How many of you would say that Popeye should be in the answer? How many of you would say that Popeye should not be in the answer? Okay. Popeye, not in the answer. Right, nobody in the answer, in fact. Okay, so far so good. Null is not greater than 8. Does that mean that null is less than or equal to 8? So you'd think it should be, right? If he's not in this query, he should be in its complement. Oh, man, he's not there either. Where's Popeye, right? This is a little weird. Right? This should cause you some pause because it's going to screw up a lot of your thinking about negating predicates and doing De Morgan's laws and stuff like that, right? Not exists something for all the negation of that thing. May not work with nulls. Yeah? Can you do a rating equals null? Aha! Let's try it. Let's say where rating equals null. All right, null's a value, so that's syntactically legal. But nobody's got the value null because null is not a value. Aha! All right, his rating is null. I don't know what value it is. It's not null. It's also neither greater than nor less than 8. So it's just unknown. All right. So this is a little weird. You have to kind of get used to this. And it affects not only comparisons, it affects other things in the language too. So let's keep going with this, and we can play with it as we go. So rating greater than null, false. What about and, or, and not? Oh, man. Okay. Let's draw some truth tables. And truth table. You guys have done truth tables, I assume, right? Except we've got a 3-valued logic now. We got true, we got false, and we got null. We got true, and we got false, and we got null. What's true and true? What's true and false? What's true and null? Well, let's hold that thought for a minute. What's false and true? False and false is false. Okay, let's face it. What's true and null? It's null. Because, look, I don't know what it is. If it's true, then it's true. So if this guy turns out to be true, then it's true. And if this guy turns out to be false, then it's false. So it's null. Okay, what about null and false? It's certainly false. It doesn't matter what this value is, right? Because anything in false is false. And null, so this is false too. And null is clearly null. All right, now you have to do this for or and not, right? Not too hard. Okay. What about sum? What is the sum of ratings? Well, let's try this out. I actually got bit by this doing either prepping for your homework or prepping for my talk at this conference this week, but this is kind of a gotcha. So, Select sum of ratings. You know what's going to happen here, right? This should be easy from Sailors. What's the sum? Well, 7, 2, 8, null. What do those add up to? Kind of seem to add up to null, right? That would make some sense, but it would be too irritating if we did that. All right, because aggregations, you could have 10 million rows in your table, some of which people were too lazy to enter the value, right? You'd still like to see the sum for the rest of them. Thank you very much. Okay, what about the average? Well, actually, okay. Select, let's try this. Count star from ratings. How many counts? What's count star? What should the answer to this be? Do you remember what's in table? Here's what's in the table. Oh. No, from Sailors. Sorry. Here we go. All right. What do you believe the answer to this is? How many people say 4? How many people say 3? It's 4. Cool. Good. You're very smart. What if I say rating? How many people say 4? How many people say 3? Ha-ha. Okay, you're beginning to see a pattern here. So what would the average be then? The average is just going to ignore, it doesn't affect the count or the sum, so it won't affect the average, right? The null, it's like the null was never there. And that is the SQL semantics for nulls and aggregation. You eliminate them before you do any aggregation. You just take them out of consideration. Okay? And the rule, so that's the rule for aggregation. You ignore the nulls before you aggregate. The rule for where clauses, for selects are, you carry all your nulls through all your logic very carefully, all your ands and your ors nested through your expression, and then at the very, very top, if the final evaluation of the expression tree is where null, what happens? Well, we can just type it. Select star from Sailors where null. It's neither true nor false, but it is a Boolean value. All right. So null at the outermost part of the where clause is treated as false. So in particular, you could say, where rating, well, here's another one. Rating equals null. There's no rating that equals null. So here, let's say where null and true, right? Null and true equals null, yeah? Right. All right, but if you say select null and true, it gives you back a null. There's a row there. All right, it's got a null in it. So it's in the select clause, it'll pass you back this null. But if you say where null, it throws away tuples. All right, so the value null is fine. It's just that if you put it in a where clause, at the very top, it evaluates to false. All right. This causes no end of difficulties when you are trying to do things like turn correlated subqueries into joins, which we won't do in this class. But that was my first job after college. It was a big hassle. We wrote a paper about it. It was fun. Okay, let's look at joins. There's different kinds of joins. You may have heard about this or asked about this at some point. There's inner joins, there's 3 flavors of outer joins, and there's natural joins, all right, which I didn't even put on this slide. So we'll just go through them. The inner join is the join you're used to. It's the theta join, all right? It's the default kind of join we've always talked about, okay? Here's 3 different queries that are the same. The first one is in the syntax we usually use, where the from clause just lists the table names, and the join predicate is listed in the where clause. The second syntax, if you prefer, you can say a sort of infix notation, sort of, where you say S inner join R, on, and then you give the join predicate. So the theta comes in the on clause of that. So it's a infix to say inner join, but it's postfix to say what it's on. All right, it's a syntax. Some people like it. It's fine. So it's equivalent to the previous one. And then this third thing, well, we saw this in SQL, right? Natural join. It's going to happily form a where clause for us of all the matching column names, right? And it's going to throw away that extra copy of the column name. So let's just do this in Postgres just to see what it looks like real quick. So here's the first version of this thing. Right, traditional. Here's the second version with an inner join syntax. All right, and here's the third version with the natural join syntax. All right, they all give the same answer. That last one, though, if we said select star, oops, I didn't want to do that. No, you can't do that. A, forward. No, come on, A. It's not going to work. Actually, there we go. Let me try this one more time. Copy, paste, paste. Thank you. Go to the beginning. No. All right, I'm not going to be able to do this. It's too much work. PSQL CS186, select star from Sailors, natural join, reserves. Notice that SID only appears once, all right, as we talked about with the algebra. SID is in both tables, but there's really no reason to keep two copies of it in the output. So you get all the columns, select star, but SID only appears once. Okay? Whereas if we did it select star with the inner join syntax, you'd get SID twice. Okay. So natural join's kind of handy if you happen to know the column names. I don't recommend using it in your code, though, because it's not very robust to schema changes. If somebody adds a new column to one of those tables that happens to match the column name in the other table, kaboom, your queries are going to start behaving really weird. So I don't encourage you to use natural join. I've actually never seen it used in the field, but it's in the language. All right. Here's some examples. I don't know that we need to go through them. This is the traditional inner join. The interesting thing to do now, though, is to talk about outer joins. All right. So the left outer join is sort of the easy one to start understanding. So what's going to happen is when we say a query like this, I want sailors, I give it a new table name, which we're not going to be able to use, unfortunately. Sailors S, left outer join, reserves R. What I want is that if there's a tuple, if there's a sailor, there's a tuple in the sailors table that has no reservations, there's no matches to it, I still want it in the output. I want to see that sailor's ID. I want to see their name. Now, they haven't reserved anything, so you can't give me a boat. So for that, give me a null. Okay, so what outer joins are going to do is, for the tuples on the left-hand side of a left outer join, that is to say sailors here, if there's matches, it shows you the matches. If there's no matches, it'll show you the columns from the sailors table and nulls for the columns from the other table. Okay? So here's an example. If we join these two tables together, and I accidentally blew these tables away before class, so I can't run this query for you. But if you join these guys together, you'll see that Dustin has a reservation, and Bob has a reservation, but Lubber has no reservation. And so the output's going to look like that. Yes?
So, let's say there was a row in the second table that was all null. So would there be any reason to not get rid of the second SID because you might want to keep the information of which rows were joined and which ones were filled and which nulls?
Well, I didn't understand that. I'm sorry. Let's try again.
So this is the second table, if we don't have something to join with, we just fill it in with all nulls.
Yes.
What if I'll reformulate it now.
Okay. Or try it out. You can insert some data in your database. All right. Okay. Hold that thought. You can do the same thing the other way, right outer join. If for some reason the thing you want to preserve is on the right-hand side of your from clause infix notation, that's fine. We'll do the obvious thing here. Here, if there are boats that have never been reserved, it'll output those boats with null reservations, right? So boat ID 102 was never reserved. Boat ID 104 was never reserved, and so they're preserved in the output. And as you might expect, there's something called the full outer join, which preserves on both sides of the join if there's no matches. All right? And so in this case, we'll get the same answer we got with the right outer join, because there actually aren't any reservations. There aren't any reservations for a non-existent boat. If there had been reservations for a non-existent boat, we would have the reservation ID and empty and nulls for the boat fields. But we can't have reservations for non-existent boats because we declared referential integrity on this table. We said if a reservation references a boat, that boat must exist. Okay. So in this particular example schema, there's no way to have a reservation that doesn't match a boat. Right. But in general, the full outer join would preserve from both sides. Good? Outer joins are super common when you're exploring data. Like you have a bunch of information about sales transactions, let's say, and you want to find out for each one the information about the customer that goes with that transaction. But maybe your customers table is missing some stuff that was in your sales transactions. It doesn't mean you don't want to see the sales transactions. It just means, you have to just say, I don't know about that customer. So it's very common when you're looking up a foreign key to do an outer join with that foreign key table, because if you don't find a match in that foreign key table, okay, you still want to see the stuff you're looking up. It's also very common when you're building web forms to be putting together data from multiple places and wanting to make sure that the cells that don't have matches at least show up in the user's eyeballs at the output. So a lot of times when you're doing data display or data exploration, outer joins are very natural. The other thing I'll point out is that inner joins are kind of nefarious. They drop data sort of silently. If you expect that for every tuple here, there's going to be a match over here, and there's not, you might do stuff wrong, like count up the result of the join or sum up some things in the join, not realizing that you lost data over here. So outer joins are really quite useful, and I encourage you to think about in almost every situation whether an outer join isn't what you want. Okay. All right. Now, you sit down and you write all these queries, and sometimes they're long, and you might want to reuse them. All right. So there's a way to give queries names, much like you give a block of code a function name in a traditional language. Here you can give a block of SQL a view name. They're called views in SQL. So you can say create view, you give it a name as, and then you give it the select statement. All right. So this makes development simpler because you can reuse code you wrote before, and you can have modularity. You can have little blocks of code that are encapsulated in a name, and you can stop thinking about them. They're often used for security because the authorization model, that is to say who gets to access what in SQL, is based on table names. So, and I'll show you an example of this in a minute. An important note is that views by default are not materialized. That means they're not stored. They're lazily evaluated at the time you use them, much like in a functional language. A function would be evaluated only at the time of use. All right, so the contents of a view are not stored. All right, if they are stored, it's called a materialized view, and some systems will let you declare materialized views. That's got its own wrinkles that we won't talk about right now. But for now, assume that views are not materialized. So here's an example of a view called reds. It's taking from the boats table and the reserves table all reservations for red boats. It's grouping it by boat ID, and then it's counting up the number of reservations for each red boat. All right, so you can think of it as the count of reservations per red boat. Some statistics about the red boats. All right? And on the next slide, for whatever reason, I changed it to red count. I apologize about that. So it's up there at the top. It should really be called reds, I guess. Here's an example of the output. And then you can reuse it in queries. You can take this reds or red count table, and you can join it against boats. You can match on boat ID here. And you can look for counts less than 10. So here I want to find boats that are red and have fewer than 10 reservations. Right? So I can use the red count for that. What do I want to say? Before we go on, I guess, am I going to talk about this later? I think I am. Yeah, I'll talk about it in a minute. Okay, good. Here's another thing you can do for encapsulation. If you don't want to define a view, after all, has a name, and it lives around forever, and other people could potentially look at it if you don't give it security. Maybe you're just going to use the query just once, but you still want a little modularity. You want to kind of tuck it aside from the rest of your query block. You can actually put your view in line in the from clause. So here's an example. Select bname, scount from boats to b, another table. What is that other table? It's a query. It's in red. And we're going to name it reds. So it's The as clause here is giving it a range variable name and also defining a schema for it. All right, so you can have column names for it, BID and scount. Otherwise, the second column of this, which is count star, might not be defined. Right? So you can throw queries into the from clause kind of on the fly if you want. Just put an as after it, and then you can reference them below. You can see in the where clause we reference reds.bid. Good? There is a third way to have these queries defined separately. It's the with clause, and it goes before your select. So this is the typical, it's also called a common table expression. I'm not exactly sure why. And so you say with, you give it a schema, as, you give it a query, and then you can say select and reference it. So it's like a locally scoped view definition. Right? It doesn't persist outside the scope of this query, but in the scope of this query, that thing is called reds. Okay, and with clauses actually are a little more readable than this stuff. I find these things are really hard to read because you got all that SQL nested inside your SQL. Here it's sort of a little more linear. You define your sort of views, temporary views if you want, and then you do your query. With clauses also, and we won't do this exactly in this class, but with clauses can be used recursively, which is really confusing. And so I won't talk about that right now. But you can actually have a with clause, define a table, and then reference that table again in the select clause recursively. So I won't talk about that right now. But it's pretty fun. Maybe we'll do that as an advanced topic lecture. Okay. But this is just the simple syntax for temporary views, essentially. You'll want to do this in your homework. So we're going to make you write a whole bunch of SQL in your next homework. And some of it's going to be complex, and you're going to want to use things like with clauses to make it more modular. All right, SQL has a very simple access control policy, which is part of the DDL, which you can grant privileges to objects. So in SQL, when you log into Postgres, you are a user, all right? And there are other users in the system, and you can grant them access to stuff. And the privileges they can have and the objects they can have are pretty simple. So the objects can be tables or views. That's it. Because those are really the only things of substance in the system. So you can give people privileges on tables or privileges on views. And the privileges can be select, insert, delete, references. Are they allowed to make a foreign key reference to this table that we promise to keep good? All right, or all, which is all the above. The opposite of grant is revoke. Okay, so you can always revoke privileges that you've given before. The with grant option is transitive. You grant them this permission, and you grant them the permission to grant the permission. Okay, so that they can do it. Users can be users. There's also a notion of groups in SQL, much like in Unix. So there's a way to give access to groups. This seems kind of clumsy, and arguably it is kind of clumsy. The thing to keep in mind is that views are actually very powerful. Like with a view, remember from the lecture on relational algebra, here's a big table, right? It's got 1 million rows and 27 columns. Using a view, I can boil it down to just one cell, right? I can create a view that selects for this row and projects to only this cell, and then that's the only thing you get to see. So I can get pretty fine-grained access control with views, all right, down to the cell level. I can also have views that do things like summarize the data. For example, I could let you see the average grade on homework 2 for all students. And I could grant access to that to all of you, but you wouldn't have access to each other's grades. You don't only have access to the average. Right? So I can actually define access control on aggregations of data, even though I don't define access control on the data. Now, you have to be pretty careful about that if you're trying to preserve privacy. Okay, so there's been a lot of kerfuffle about this over time, but the standard example is, suppose that I gave you access to certain data grouped by a whole bunch of things and then counted. And the certain data was, let's say, occurrences of AIDS. Okay, because this, I think, example happened. So occurrences of some disease that you might not want people to know you have for insurance reasons or whatever. And the group bys were things like county. Okay, and if you can select this data set down to find me, there's only one person in this county. There's one occurrence of AIDS in this county, and there's only one person in the data set in that county, then you know who is the person who has the disease, right? So you have to be a little bit careful that people can't figure out individual information from statistical information, which in general is a hard thing to protect against. Whew. That was a giant sub point. The general point, though, with SQL is you can define these privileges on any arbitrary SQL you like, including aggregations. Okay. A couple more important, useful topics that we'll do today before we get into the juicy stuff on Thursday. Constraints, and then embedding SQL in programming languages. Okay. There's the opportunity in SQL to define what are called integrity constraints on your data. And an integrity constraint is a Boolean expression that every legal instance of the relation must satisfy, which means that if you try to insert or delete or update the database in a way that violates the integrity constraint, the database will reject your insert, delete, or update. So the database is going to promise to maintain these constraints for you. Okay? So these are often very useful for ensuring application semantics. Like, let's make sure that the Sailor ID is a real key. Because if SID is not a key, a whole bunch of my app logic will break. I mean, I'm assuming this is essentially the name or the unique address of the Sailor. And if it's not unique anymore, things are going to kind of blow up. So that key constraint that we put in, that primary key clause that we put in that create table statement, is a form of integrity constraint. All right? Similarly, the referential integrity constraints. Well, we're going to do that in a second. Another thing you can do is you can prevent inconsistencies, like the Sailor name has to be a string. All right? Let's make sure that's always true. Or age has to be less than 200. You can have constraints like that as well. So you can have constraints based on some values that you understand in the domain. So the types of the constraints that we'll look at, the types of integrity constraints we'll look at, domain constraints, which are that the field values must be of the right type. So when you create a schema, if you have a column of type integer, you cannot put a string in that column. That's called a domain constraint. The domain of that column is integer. Right? The database will always enforce that for you. So SQL schemas kind of come with domain constraints. Primary key constraints, we just talked about, will be enforced by the database. Foreign key constraints are also enforced. So if you say reserves has a foreign key to sailors, that means you cannot have a reservation for a sailor that doesn't exist. And the database will enforce that. Right? So that foreign key constraint from reserves to sailors that we saw early on in the first few slides of today's lecture, right? Here's the reserves table. It's got an SID and a BID and a date. And here's the sailors table. It's got an SID and a name. Logically, when we said there was a foreign key from reserves to sailors, and this was the foreign key, what we were saying was that for every cell in the SID column here, it's pointing to a particular sailor. This is the primary key of sailors. This is a foreign key to it. And referential integrity is this foreign key constraint that this reference, this foreign key, must point to a valid sailor. Okay. And then you can have general constraints, which you can just define anything, really. And I'll show you that in a minute. Before we look at the examples, where do these integrity constraints come from? All right. They come from the programmer trying to capture the semantics of the real world. So the reason you built a database, damn it, was because you wanted to keep track of some stuff. And that stuff mattered to you somewhere, somehow. Okay? And when you wrote down what the stuff looks like, hopefully, if you were careful, you wrote down some rules about the stuff. Like, your bank balance cannot be less than 0. Why? Because that's how the bank works. Okay? You cannot have two biological mothers. Why? Because that doesn't happen in nature. Does the computer care? No, the computer doesn't care. You have to tell the computer. Okay? If you give the computer a data set with a person with two mothers, what's the computer supposed to do? Well, if you don't tell the computer, that sounds fine, right? If you tell the computer, then it should do something about it. So the note is we can check these integrity constraints on an instance. I give you a database. I give you an integrity constraint. You can tell me, is this database legal or not? Is there a person in here with two biological mothers? If so, it's illegal. All right? But you can't infer an integrity constraint by looking at an instance. Suppose I give you a database instance, and everybody's first name is Bob. That does not mean that first name shall always be Bob. Okay? Just because I give you a table where something is true doesn't mean it must be true. Integrity constraints have to be written down by a person with intent. All right? We don't mine them out of data. You can mine them out of data, which is interesting, but generally speaking, not correct, right? It might be worth doing because you're curious what's in this data, but that doesn't mean it's what you want. Okay. Key and foreign key integrity constraints are the most common ones you'll use. And then, more general integrity constraints will be supported too. Putting in your primary keys is super important and useful. So you really don't want to get duplicates where you don't want them in your tables. Strongly encourage you to put in primary key constraints. Foreign key constraints are nice too. Sometimes they're a pain because the database enforces them when you don't really want it to enforce them. You'd be perfectly happy to have a dangling reference, in essence, and you're annoyed that the database is not letting you. Okay, so keys, key constraints. Keys are a way to associate tuples in different relations, right? So here's enrolled and students. It's a different example. In the enrolled table, we have SIDs. In the students table, we have primary keys that are SIDs. Okay, and the enrollment records are pointing, in essence, to the students table, right? So that's a primary key. That's a foreign key. All right, primary keys. Now let's be a little careful. And we'll review this again next time, but let's end with a little definition. A set of fields, we'll call it a superkey. A superkey. If no two distinct tuples can have the same values in all its fields. Okay? So any collection of fields that can serve as a unique identifier for a row is a superkey. Now a set of fields is a key if it's a minimal superkey. That is to say, it's a superkey and no subset of the fields is a superkey. You need every one of those fields to make it be a superkey. Then it's a key, not just a superkey. So superkeys are kind of sloppy. Keys are you can't take anything away from them. Okay. Can you have more than one key for a relation? Sure you can. So for example, in a student's database, we might have SID and email. And we might have, a pretty reasonable view of the world that emails can't be used by two people. Okay, so those might both be keys. And one of them will just get chosen arbitrarily by the database administrator to be the primary key, all right? And they'll name it as such. They'll say primary key and SID, okay? The other key is referred to as a candidate key. It's a key. It's not just a super key, but it's also a real key. It's minimal. It's just not the primary key. It's another one of the candidate keys. So SID is a key for students. Name. Would name be a good key? Even first name, last name, is that a good choice for a key? It's not, right? There's other Joseph Hellersteins in the world, and I'd hate to prevent them from taking my class. Right? For example, there's very few, though. It's only like 180 people with the name Hellerstein in America. I looked it up the other day. It's exciting. The set SID GPA, you might want to be a super key. It probably is a super key, right? Because SID is a key. So SID GPA is a super key. But SID all by itself is also a super key, and it's a key because it's minimal. Make sense? All right, I think we're out of time for today. We'll come back on Thursday. Just a note, I will not be here. I'm going to be at the Strata Big Data Conference down in San Jose. Professor Franklin is going to sub for me. He knows SQL pretty well, so he should be able to pick up from here. If you have questions and you feel that he didn't answer them satisfactorily, let me know or let the TAs know, and we'll sort you out. I will see you next week. Homework is being passed out tonight. It will exercise your SQL. Talk to you soon.